So in video 6, we're going to do a couple practice problems that involve the use of weak acids and weak bases to give you an idea of what you can expect, and also introduce this concept of percent ionization, which really won't be new to most of you. We're just calling it something different, and you'll see what I mean when we get to it. Okay, so here's a typical problem that you'll see for Ka. So I have a pH of a solution, it's 0.10 molar of formic acid at 25 degrees, and its pH is 2.38. And it wants me to calculate the Ka at this temperature. So we know that the Ka expression is the acid concentration times the conjugate base divided by that weak acid's concentration. So if we look at that, to calculate the Ka, I need to know all those three concentrations at equilibrium. And I could find the acid concentration, which is equal to the formate ion concentration. I can get that information directly from the pH. So the pH is the negative log of the acid concentration, and if I solve this equation going down the line looking at this, so 10 to the minus pH, or 10 to the minus 2.38, is the acid concentration, which is also equal to the formate ion concentration. And when we crunch those numbers, we come out to be 4.2 times 10 to the minus 3 molar, and that's something that is not in this slide that should be. We need the units for that. Okay, so with this information now, I can backtrack, use my K expression, and pop these numbers in. I'm going to do that with an ice chart just for clarity. So the change in this is going to be minus x. And that minus x, I already know what it is. It's the 4.3 or 4.2 times 10 to the minus 3. Okay? So I'm going to lose that much, and I'm going to gain that much over here. Oh, geez. It's just not working. Okay, and at equilibrium, again, I'm going to use the approximation, so this value is not going to change. The number I'm subtracting is very small, and it's not going to matter. And then I got 4.2 times 10 to the minus 3, 4.2 times 10 to the minus 3. And when I go into this expression, pop those values into the Ka, crunch the numbers, I get a Ka of 1.8 times 10 to the minus 4. All right, so using the same information, we're going to solve for the percent ionization of that. And really, percent ionization is how much is dissociated. So pick one of the ions, that ion divided by that concentration you started with, times of 100 is the percentage that's actually ionized. And this may look familiar to you because this is really the 5% rule. So using the same numbers that we had before, I calculate the concentration of acid, which is 4.2 times 10 to the minus 3. My initial concentration of that acid is 0.10 molar. And taking that 4.2 times 10 to the minus 3, dividing it by 0.1, multiplying that by 100, gives me 4.2% ionized in this problem. So again, the percent ionization, the ions that I have divided by the total concentration times 100 gives me that percent ionization, which really is that 5% rule that we've already talked about. All right, another example. I want to find the pH of a 0.15 molar solution of ammonia. So the first thing I need to do is write down the reaction. What is ammonia going to do in water? It's going to react with water to give me ammonium ion plus hydroxide ion. This is a weak base, so I can write a Kb for this reaction. Remember, I don't include the water in it. So it's the ammonium ion concentration times the hydroxide ion concentration divided by the ammonia concentration. And I could look that number up in the table, and it's 1.8 times 10 to the minus 5. I could set up an ice chart. I have an initial concentration of ammonia, and I have no ammonium and no hydroxide when I first start this reaction. The change, I'm going to lose some of my ammonia. I don't know how much. I'm calling it X. Plus X for the ammonium plus X for the hydroxide. So at equilibrium, I'm going to have 0.15 minus X. And again, since the K is small, I'm going to use the approximation and say that that's equal to 0.15. I have to make sure I go back and check, and then I'll have X and X over here. And those numbers into the KB expression, I get 1.8 times 10 to the minus 5 equals X squared divided by my 0.15, and solving for X, I wind up with 1.6 times 10 to the minus 3. But that X is not the acid concentration, it's the OH minus concentration. And this is common mistake that people make. Write down what X equals. All right, so X equals my hydroxide ion concentration, which is 1.6 times 10 to the minus 3 molar. So I can calculate the pOH by taking the negative log of that, and that gives me 2.80. And if I subtract that number from 14, because remember that the pH plus the pOH has to equal 14, I get 11.20. And this makes sense. 11.20 is basic, and I'm putting a base in solution, so I expect to get a value that's on the basic side.